Hold a magnet near your refrigerator and you feel a force you cannot see, a pull living in empty space. Now shrink that magnet down past anything you could ever hold, down to a single particle called the muon, a heavier, short-lived cousin of the electron. That tiny particle is itself a tiny magnet, and physicists have measured its strength to 12 decimal places, and for more than 20 years, the last few digits sat just far enough from what the equations predicted to look like a real crack in everything we know. If you like following a true mystery all the way to its end, take a moment to subscribe, and we will keep going. That number has a name, the muon's anomalous magnetic moment, what physicists write as G-2. We will build up to it slowly, one plain step at a time, starting from what a magnet even is. And we'll end on a strange question. How does a crack in physics simply disappear? Take a small magnet off your refrigerator and hold it near the steel door. You feel something before the two ever touch. There is a pull in the gap, a force reaching across plain air. We're so used to this that we forget how strange it is. Nothing you can see connects the magnet to the door, and yet the pull is real, and it grows as the gap closes. Now picture a spinning top on a table. As it slows, it does not simply fall over. It leans, and the lean itself starts to circle, tracing a slow cone in the air. That circling of the tilt has a name. Physicists call it precession, and it is the quiet thread that runs through this whole story. A magnet and a spinning top seem to have nothing to do with each other. Put them together in the right object, though, and something useful happens. A tiny magnet that also spins will wobble when you place it in a magnetic field, and the speed of that wobble tells you exactly how strong the little magnet is. That single fact sits at the center of everything we're about to follow. The object we'll follow is one particle. It is called the muon. You have never seen one and never will, because it lives for only about 2/millionths of a second before it falls apart. In that flicker of time, billions of them are passing through your body right now, born high overhead where cosmic rays strike the upper air. The muon is a heavier, short-lived cousin of the electron. Like the electron, it carries electric charge, and it spins. That makes each muon a minute magnet, turning in place, ready to wobble. Here is the part that is hard to believe. Physicists have measured the strength of that wobble, the strength of the muon's own tiny magnetism, to 12 decimal places. 12. If you measured the distance from your home to the far side of the moon, that precisely, you would be left arguing about the width of a single human hair. The number they pin down is one of the most exact things any person has ever learned about the physical world, and for more than 20 years, that number sat in an uneasy place. The equations of physics make their own prediction for it. When you write out the rules we believe govern reality, and ask them what the muon's wobble should be, you get an answer. The measured answer and the predicted answer agreed almost perfectly. Almost. They parted ways far out in the last digits, in a gap so small you could overlook it, and so stubborn that you could not. That tiny gap is the anomaly in the title. For 2 decades it looked like the most promising crack in our entire picture of nature, the one place where the known rules might finally break and let something new slip through. Careers were built on it. A massive experiment was rebuilt and hauled across a continent to chase it. People genuinely lost sleep over those final few digits. Then, across the spring and summer of 2025, the gap closed. There was no new particle caught in a detector, no flash in the dark. The crack that had kept physicists awake simply went away, and the way it went away surprised nearly everyone. To see how a number can do that, you first have to understand the number itself. You have to know what a magnet really is, what spin really is, and why a particle that lives for 2/millionths of a second became the sharpest test we have of the laws of the universe. So we start where the wobble starts, with the plainest question there is. What makes a magnet, and why would a particle ever spin into one at all? The answer begins with where the muon came from, and with the moment a great physicist threw up his hands and asked who had ordered it. In the 1930s, the most powerful particle source on Earth was the sky. Long before there were giant accelerators, physicists carried their instruments up mountains and floated them on balloons to catch the rain of high-energy particles that pours down on us constantly from space. We call that rain cosmic rays. When those particles smash into the top of the atmosphere, they shatter into showers of new particles, and some of those reach the ground. Carl Anderson was a young physicist at the California Institute of Technology with a gift for building cloud chambers, sealed boxes in which a charged particle leaves a thin trail of droplets, like the line a jet scratches across the sky. A magnetic field bends those trails, and from the bend you can read a particle's charge and roughly its mass. Anderson had already used this trick to discover the positron, the electron's antimatter twin, a find that helped earn him a share of a Nobel Prize while he was still in his early 30s. In 1936, working with his student Seth Neddermeyer, Anderson noticed tracks that did not fit anything known. The particle bent in the field too gently to be an electron, yet too sharply to be a proton. It sat in between, with a mass around 200 times that of the electron. It was something genuinely new, a middleweight particle nobody had asked for. At first, the discovery was tangled up with a prediction. A few years earlier, the Japanese physicist Hideki Yukawa had argued that the force holding atomic nuclei together must be carried by a particle of roughly this weight. When Anderson's middleweight particle turned up, many assumed it was Yukawa's carrier of the nuclear force. It took the better part of a decade and careful experiments in Italy during the war to show that the new particle barely felt the nuclear force at all. It was not Yukawa's particle, it was simply a heavier electron, and it had no obvious job to do. That uselessness is exactly what made it famous. The story, often repeated, is that the physicist Isidor Isaac Rabi heard the news, paused, and asked, "Who ordered that?" The line stuck because it captured a real unease. The electron made sense. It built atoms, carried current, held chemistry together. This new particle did none of that. It was just a fat, fragile copy of something the universe already had, and no one could say why nature would bother to make it. We named it the muon, after the Greek letter mu. We now know it is one of 3 charged particles in the same family, the lightest being the electron, and the heaviest a particle called the tau. They are identical in every way we can find except for their mass. The muon weighs about 207 times what the electron weighs, and that extra weight comes at a price. A muon is unstable. Left alone, it survives for about 2 2/10 millionths of a second before it decays, usually into an electron and a pair of nearly weightless particles called neutrinos. 2 millionths of a second sounds like nothing, and by human standards it is. But these particles travel so close to the speed of light that, by a real effect of Einstein's relativity, their internal clocks run slow from our point of view. That stretched lifetime is the only reason cosmic ray muons survive the long fall through the atmosphere to reach the ground, and your hand at all. So we have our character. It is charged, so it can be pushed by electric and magnetic fields. It spins, so it behaves like a tiny magnet. And it lives just long enough to be caught, stored, and watched. To turn that into the most precise test in physics, we need the next idea. We need to understand why anything that spins and carries charge becomes a magnet in the first place. Lay a loop of wire on the table and run a current around it. A magnetic field springs up through the loop, as if a small bar magnet had appeared there, with a north end and a south end. Move the loop near a compass and the needle swings. This is one of the deepest facts in physics. Moving electric charge makes magnetism. A current going in a circle is a magnet. Full stop. Now shrink that loop down to a single particle. An electron or a muon carries charge, and it also has a property we call spin. The name is a gentle lie that helps at first. You can picture the particle as a tiny ball turning on its axis, with its charge whirling around like current in a loop. By the loop rule, that whirling charge should make the particle a small magnet, with a strength and a direction set by how fast it spins. For our first picture, that is close enough, and it points the right way. We measure how strong that little magnet is with a single number. Physicists call it the G factor, Think of it as a dial that sets the magnet's strength for a given amount of spin. Turn the dial up and the same spinning particle becomes a stronger magnet. Turn it down and it becomes weaker. Everything in this story is, in the end, an argument about exactly where that dial sits. If the spinning ball picture were the whole truth, you could work out the dial from plain physics. Treat the particle as a little charged sphere whirling around, add up the current, and you would expect the G-factor to come out to 1. A spin of a certain size should give a magnet of a matching size in simple proportion. That was the natural guess in the early days, and it was wrong. When physicists actually measured the electron in the 1920s, the dial did not read 1, it read close to 2. The electron was twice as strong a magnet as the spinning ball picture said it had any right to be. For its amount of spin, it produced double the magnetism the simple model predicted. This was a real shock, not a rounding error. A factor of 2 is enormous. It meant the comfortable picture of a charged ball spinning on its axis was missing something important about what spin truly is. Spin is not a particle physically rotating like a top, even though that image got us this far. It is a built-in property, as basic to a muon as its charge or its mass, and it does not obey the tidy rules of a spinning sphere. The image was a ladder. We had now climbed high enough to feel it wobble, so by the late 1920s physics had a clean experimental fact and no clean reason for it. The electron's magnetic dial sat at 2, not 1, as the loop of current picture begged for, but 2, almost exactly. Whatever theory could explain spin properly would have to deliver that 2 on its own, without being told the answer in advance. A good theory should not just match the number, it should force it. Keep that target in mind, because it is about to be hit with startling grace. The whole muon story is the slow refinement of this one dial, the G-factor, pushed to more and more decimal places by sharper experiments and deeper theory. Right now, the dial reads, as far as anyone can tell, exactly 2. In the next step, a young theorist will write down an equation he was not even building for this purpose, and that equation will hand back the 2 on its own, as if the universe had been waiting for someone to ask the question the right way. In the late 1920s, a quiet young Englishman named Paul Dirac set out to solve a problem that had nothing to do with magnetism. He wanted to write an equation for the electron that respected 2 great theories at once. One was quantum mechanics, the new physics of the very small. The other was Einstein's relativity, the physics of things moving near the speed of light. The existing equation worked for slow electrons but broke when they moved fast. Dirac wanted one law that held in both worlds. Dirac was famous for his silence. Colleagues joked that his unit of speech was 1 word per hour. He trusted the beauty of mathematics more than almost anything, and he searched for an equation that was not just correct but clean, with no ugly patches. After a long effort, in 1928 he found it. The Dirac equation is still written on the wall of Westminster Abbey near his memorial, in honour of what it opened up. The equation did things Dirac had not put into it by hand. That is the mark of a deep law. You ask it one question, and it answers 3 more you had not thought to ask. The first surprise was antimatter. The math demanded a partner for the electron with the same mass and opposite charge, a particle nobody had seen. Within a few years, that was exactly the positron Carl Anderson found in his cloud chamber. The equation had predicted a whole new form of matter before anyone caught it. The second surprise is the one we came for. Spin fell out of the equation on its own. Dirac had not assumed the electron was spinning. He had simply demanded that his law respect relativity and quantum mechanics together, and out came a particle that must have spin of just the amount measured. Better still, the equation told you how strong a magnet that spin would make. It set the dial, and the value it gave was 2. Sit with how strange that is. The earlier picture of a charged ball spinning on its axis predicted a dial reading of 1, and experiments stubbornly showed 2. Physicists had no honest reason for the doubling. Then Dirac wrote down an equation aimed at a completely different goal, never mentioning magnets at all, and the doubling appeared by itself. The G-factor came out to exactly 2, with no fudging, no extra assumption, no hand placed on the scale. The universe handed back the number that had been a mystery for years. This is one of the great moments in the history of physics, and it is worth marking plainly. A correct theory does not just fit the numbers you already have, it produces them for reasons from a deeper place. Dirac's 2 was not measured and then explained. It was forced by the structure of the equation, and the measurement only confirmed it. For a while it looked as though the question of the electron's magnetism was simply finished. The dial read 2. The equation said 2. There was nothing left to argue about. Dirac himself was modest about it in the strange, flat way that was his alone. He treated the success as the natural reward for trusting good mathematics, and he moved on to other puzzles. He could not have known that the very precision of his 2 was about to become the problem. Because the better physicists got at measuring the electron's magnetism, the more they would find that the dial did not sit at exactly 2 after all. It sat at 2 and a tiny bit more, and that tiny bit more, that small excess past Dirac's clean answer, is the seed of the entire anomaly. To find it, 2 experimenters at Columbia University were about to push their measurement just 1 decimal place further than anyone had managed before. After the Second World War, the centre of gravity in physics shifted toward the United States, and one of its busiest rooms was at Columbia University in New York. Physicists there had spent the war years sharpening a set of tools, radio waves, microwaves, and the careful art of measuring frequencies with great precision. When the fighting ended, they turned those tools on the atom, and they began to measure things more finely than anyone ever had. 2 of them were Polycarp Cush and Henry Foley. Cush was an exacting experimenter, blunt and demanding, who later said he simply wanted the numbers to be right and did not much care whose theory they helped or hurt. Working together in the late 1940s, he and Foley set out to measure the electron's magnetism, not to 1 or 2 digits, but far more precisely, by watching how atoms responded to magnetic fields. Their method rested on a simple idea. Place atoms in a magnetic field, and their internal energy levels split, like a single note dividing into 2 slightly different tones. The exact spacing of those tones depends on how strong the electron's little magnet is. Measure the spacing of the tones with enough care, and you read off the G-factor directly, with a precision the old methods could not touch. In 1947, they got their answer, and it did not match Dirac. The dial did not read 2. It read about 2 2/2000ths. The excess was small, a fraction of a percent, but their measurement was sharp enough that it was no accident and no mistake. The electron was a slightly stronger magnet than Dirac's clean equation allowed. This was unsettling in a precise way. Dirac's equation was not a rough sketch. It was an exact law, and it said 2, exactly 2, with no room for a little extra. Now careful experiment said the truth was 2 plus a sliver. Either the beautiful equation was subtly incomplete, or something was nudging the electron's magnetism beyond what the equation by itself described. There was no way to wave the sliver away. The size of the sliver mattered enormously. Cush and Foley found the dial sat about 1 part in 1,000 above 2. In plain terms, the electron was roughly 0.1% more magnetic than predicted. That is a tiny push, far too small to notice in everyday life, yet far too large to be measurement error in their careful hands. Something real was adding to the electron's magnetism in a small and definite amount. Physicists gave this small excess its own name and its own quantity. They defined the anomaly as the amount by which the dial exceeds 2, divided by 2, so that a perfect Dirac electron would have an anomaly of exactly 0. The electron's anomaly was small, close to 1 part in 1,000, but it was not 0, and that changed everything. The interesting physics was no longer in the big number 2. It had moved into the sliver past it. This is the quantity that the rest of our story chases, first for the electron and then, far more sharply, for the muon. We even have the shorthand for it now. People speak of G-2, because subtracting the Dirac value of 2 leaves you with exactly the excess, the anomaly, the part the simple equation cannot explain on its own. So by 1947 the puzzle was set, but it was upside down. The mystery was no longer why the dial sat at 2. Dirac had answered that. The mystery was why it sat a hair above 2. And within a single year, a brilliant and notoriously fast-talking young theorist would calculate that hair from scratch and get it almost exactly right. The man who explained the sliver was Julian Schwinger, and in almost every way he was Dirac's opposite. Where Dirac was silent, Schwinger was a dazzling talker who lectured without notes in long, flowing sentences. He worked at night and slept through the day. He drove a fast car, and he carried in his head one of the most powerful mathematical minds physics has ever produced. In 1948, he turned that mind on the electron's small excess of magnetism. To follow what he did, you need one new picture. In the older view, the electron sat alone in empty space, a single charged speck. The new physics that Schwinger helped build, called quantum electrodynamics, said empty space is not empty, and the electron is never truly alone. Around every electron there is a constant brief flicker of other particles popping into being and vanishing again, too quickly to catch. The electron is always dressed in this restless cloud. That cloud is the key. When you measure the electron's magnetism, you are not measuring a bare electron. You are measuring the electron together with the flickering cloud around it, and the cloud adds its own small contribution to the magnet's strength. Dirac's equation described the bare particle and gave the clean 2. The cloud is what pushes the dial a sliver higher. Schwinger's task was to calculate exactly how big that first push from the cloud should be. The calculation was hard, but the answer was astonishingly simple. The leading nudge to the anomaly, Schwinger found, was a single number built from constants physicists already knew. It was the fine structure constant, the number that sets the strength of the electromagnetic force, divided by 2 times pi. The fine structure constant is close to 1 part in 137, a number that turns up all over physics. Divide it by 2 pi and you get about 1 part in 860. Compare that to what Cush and Foley had measured. The experiment said the electron's anomaly was close to 1 part in 1,000. Schwinger's clean formula, the fine structure constant over 2 pi, gave almost exactly that same small number, with no free parameters to tune. He had calculated the mysterious sliver from first principles, and it matched the measurement. The cloud was real, and its first whisper could be computed. Schwinger was so proud of this result that the formula, the fine structure constant over 2 pi, is carved on his headstone. It is a fitting monument, because that single short expression marks the moment theory and experiment met at the level of the sliver, not just the big number. Dirac had explained the 2. Schwinger had explained the tiny bit more. This is also where the language of the rest of our story locks into place. The anomaly is the excess of the dial past 2, written as G-2/2. Its first piece is Schwinger's term. But Schwinger had only computed the leading nudge, the simplest, most likely flicker of the cloud. The cloud has rarer, more complicated flickers too, and each of them adds its own smaller correction further out in the decimals. To match ever sharper experiments, theorists would have to compute those too, term after term, deeper and deeper into the cloud. That program, computing flicker after flicker of the quantum cloud to ever higher precision, would occupy some of the finest minds in physics for the next 70 years. It would eventually require thousands upon thousands of separate pieces and the help of computers. But before we climb that mountain, we need to look honestly at the cloud itself. What are these particles that flicker into being around the electron? Where do they come from? And in what sense can empty space be full of things that never quite exist? Picture the calmest, emptiest place you can imagine. A box in deep space far from any star, with every speck of matter pumped out and every ray of light shut out. Cool it to the lowest temperature allowed. Common sense says that inside that box there is nothing at all, a perfect and motionless void. Common sense is wrong, and the way it is wrong sits at the heart of this story. Quantum physics does not allow perfect stillness. There is a basic rule, called the uncertainty principle, that forbids any part of nature from having an exactly fixed amount of energy over an exactly fixed stretch of time. The two cannot both be pinned down at once. Over very short intervals, the energy in even the emptiest box is not allowed to sit firmly at zero. It must shimmer, borrowing and repaying tiny amounts in fleeting instants. Where energy shimmers, particles appear. Einstein taught us that energy and mass are two faces of one coin, so a brief flicker of borrowed energy can become a brief flicker of actual particles. In the empty box, pairs of particles wink into being, an electron and a positron, say, or a flash of light, and then vanish almost instantly, paying back the borrowed energy before the universe can object. They are called virtual particles, and the restless sea of them is the quantum vacuum. You can picture the vacuum as the surface of a pond on a still day. From a distance it looks flat and dead. Up close it is never quite at rest. There is a constant fine froth of tiny ripples appearing and smoothing away, too small and too quick to see from the bank, but always there. The vacuum of space is like that froth, except the ripples are pairs of particles, and they are happening at every point all the time, including the space around every electron and every muon. Now bring our charged particle back. A muon sitting in this froth is constantly surrounded by virtual particles flickering near it. Some of them carry charge, so they feel the muon and respond to it. For the brief instant they exist, they take part in the muon's magnetism, adding their own small pull and twist before they vanish. The wobble we measure is the wobble of a muon wrapped in this living cloud, not a bare muon in true emptiness. This is why Schwinger's calculation worked. He was computing the first and simplest froth, a single virtual flicker around the electron, and adding its small effect to Dirac's bare 2. The match with Cush and Foley's measurement was the froth caught in the act. Empty space had reached out and nudged the electron's magnetism by 1 part in about 800, and a young theorist had predicted the nudge before looking. Here is the part that turns this from a curiosity into a tool. The exact size of the cloud's effect depends on which particles can flicker in it. The froth is not made of one ingredient. It can contain any particle the universe allows, as long as energy is borrowed and repaid in time. Light, electrons, heavier particles, even particles we have not yet discovered, all of them can take their turn in the froth around the muon, each adding its own tiny mark to the wobble. So the wobble is a kind of listening device. Measure the muon's magnetism precisely enough, and you're taking a census of everything that flickers in the vacuum around it. Every particle in nature, known or unknown, leaves a fingerprint in that number. If there is something out there we have not found, something heavy and hidden, it should still join the froth now and then, and shift the wobble by a sliver. That is the whole strategy laid bare. To find the unknown, measure the known with absurd precision, and watch for a gap. Before we point that device at the muon, though, we should see how stunningly well it already works on the muon's lighter cousin, the electron, where theory and experiment now agree to a depth that is almost hard to believe. Return to the electron and to that flickering cloud around it. Schwinger had computed only the first and simplest flicker, but the cloud has rarer events too, where 2 virtual particles appear at once, or 3, each arrangement a more elaborate way for the vacuum to froth around the electron. Each kind of flicker adds a smaller and smaller correction to the anomaly, further out in the decimals. To predict the electron's magnetism precisely, you must add them all up, term after term. Over decades, theorists did exactly that. They organized the calculation around simple cartoons called Feynman diagrams, named for Richard Feynman, who shared a Nobel Prize for this whole framework with Schwinger and the Japanese physicist Shinichiro Tominaga. Each diagram is a little picture of one way the cloud can flicker. The simplest diagram is Schwinger's. The next set is more tangled, the set after that more tangled still, and the number of diagrams explodes as you go deeper. The work became staggering. Counting the contributions where 5 separate virtual events happen at once, means drawing and computing more than 10,000 distinct diagrams. No human could do that by hand in a lifetime, so physicists wrote computer programs to generate and evaluate them. One physicist in particular, Toichiro Kinoshita, spent much of his long career pushing this calculation further than anyone, carrying the electron's predicted anomaly out to an almost absurd number of decimal places. On the other side stand the experimenters who trap a single electron in a small electromagnetic cage and watch it for months. By measuring the frequencies at which the lone electron flips and wobbles, they read its magnetism with breathtaking care. The current measured value of the electron's anomaly is known to about 12 significant figures, one of the most precise numbers in all of science. Now lay the two side by side, the prediction from the mountain of diagrams and the measurement from the single trapped electron. They agree, not roughly, not to a few digits, but out to around 10 or 11 matching figures, the two numbers marching in step far past the point where any reasonable person would expect human theory and human apparatus to keep pace. It is often called the most precise agreement between theory and experiment in the history of physics. Take a breath and feel the size of that. A physicist sat down and computed from the froth of empty space what an electron's tiny magnetism should be, and got a number. Another physicist trapped a real electron and measured the same magnetism. The two numbers match to about 1 part in a trillion. The picture of an electron dressed in a flickering quantum cloud is not a vague story. It is right, to a depth almost no other idea in science can claim. This success is the quiet foundation under everything that follows. It tells us that quantum electrodynamics, the theory of charged particles and light, is essentially flawless. When the cloud around the electron contains only the familiar particles, light and electrons and the rest, theory nails the measurement. There is no room left for a surprise. The electron's wobble has been weighed and found to hold no secrets, and that is precisely why physicists wanted more. A test that always passes can comfort you, but it cannot lead you anywhere new. The electron's anomaly agrees so perfectly because the electron is light, and a light particle mostly summons light, familiar partners into its cloud. The heavy, hidden, undiscovered things, if they exist, almost never flicker around an electron. The electron is a superb confirmation and a poor explorer. To go exploring, you want a particle that pulls heavier company into its cloud, a particle whose wobble can feel the rare, massive flickers an electron would miss. That is the muon. It is the same kind of particle as the electron, with the same charge and spin, but it is more than 200 times heavier, and that single difference turns it from a confirmation into a probe. The next step is to see exactly why extra mass should let the muon hear what the electron cannot. Why should making a particle heavier let it sense things a lighter one cannot? The answer comes straight from the froth around it. Remember that any particle can flicker briefly into the cloud, even a very heavy one, as long as the borrowed energy is repaid in time. Light familiar partners flicker easily. Heavy exotic partners flicker only rarely, and they leave only a faint mark. How faint depends on the mass of the particle doing the probing. There is a rough rule that captures it. A heavy hidden particle's effect on the wobble grows with the square of the probing particle's mass. The muon is about 207 times heavier than the electron. Square that, and you get a factor of around 43,000. So the muon is something like 43,000 times more sensitive than the electron to the rare, heavy flickers in the vacuum. Where the electron hears a whisper, the muon hears a voice. Picture two microphones in a noisy room. One is cheap and dull, the other exquisitely sensitive. Both pick up the loud conversation nearby perfectly well, and on the loud sounds they agree completely. But only the sensitive microphone catches the faint scrape of a chair in the far corner. The electron is the dull microphone, flawless on the loud, familiar froth and deaf to the rest. The muon is the sensitive one, able in principle to register the faint contribution of something heavy and hidden. This is the reason the muon, that seemingly pointless particle nobody ordered, became the most prized tool in this corner of physics. Its uselessness for building atoms is beside the point. What matters is its weight. The muon is heavy enough to feel the deep vacuum more keenly than the electron ever could, and still light enough and long-lived enough to be made in beams and stored in a ring and measured with great care. It sits in a sweet spot nature seems to have left open. There is a catch, and it is the catch that drives the whole rest of the story. The muon's heightened sensitivity cuts both ways. Because it can feel heavier flickers, its predicted anomaly includes contributions from particles that barely touch the electron. To compare prediction with measurement at the muon's level of precision, theorists must account for every kind of flicker the muon can summon, not just the easy electromagnetic ones, but the heavier and messier partners too. The muon hears more, so there is more to compute, and some of it is genuinely hard to get right. So the muon's gift and the muon's curse are the same fact. Its mass opens its ears to the deep vacuum, which is exactly what makes it a probe for new physics, and exactly what makes its prediction a brutal calculation. The electron's anomaly is hard but clean, because only familiar light partners matter. The muon's anomaly is hard and dirty, because the whole zoo of particles, including the ones bound by the strong nuclear force, gets a say. Keep that division in mind because it organises everything ahead. The muon's predicted wobble is built from several distinct kinds of flicker, and they are not equally trustworthy. Some can be computed with the same blazing precision as the electrons. Others involve the strong force, which refuses to sit still for a clean calculation, and those pieces carry almost all of the uncertainty. The famous anomaly and its sudden disappearance lives entirely inside that messy corner. Before we can understand how the gap opened and then closed, we have to see clearly what goes into the muon's predicted number. We have to lay out the full recipe, every ingredient that the muon's wobble depends on, and mark which ones are clean and which ones are trouble. Only then will it be clear why, for 20 years, the trouble looked like a discovery, and why, in the end, it was something quieter. The Standard Model is our best inventory of the particles and forces that make up the world. It is not a single equation but a careful list. 3 families of matter particles, the forces that bind them, and the Higgs field that gives many of them mass. When theorists predict the muon's anomaly, they are really asking the whole Standard Model one question. Given everything you contain, how much should you nudge the muon's wobble past Dirac's clean 2? The answer arrives in 3 pieces, and it helps to picture them as 3 separate contributions to one running total. Each piece comes from a different kind of partner flickering in the cloud around the muon. Added together, they form the full prediction that experiments are checked against. The drama of the last 20 years lives in how well or how poorly each piece can be pinned down. The first piece is the electromagnetic one, the same kind Schwinger computed for the electron. Here the cloud contains photons, the particles of light, and electrons and other muons, all the familiar charged partners. This is by far the largest contribution to the anomaly, and the very best understood. It can be calculated with the same staggering precision that made the electron's prediction match to 1 trillion parts. On this piece, theory is rock solid. The second piece comes from the weak nuclear force, the force behind certain kinds of radioactive decay. Its carriers are heavy particles called the W and the Z, joined by the Higgs. These are massive, so by the rule from the last chapter they flicker into the muon's cloud only rarely, and their effect is small. But the muon is heavy enough to feel them, and the calculation, though delicate, is under good control. This piece is tiny but trustworthy. The third piece is the troublemaker, and it deserves a plain name. It comes from the strong nuclear force, the force that binds quarks into protons, neutrons, and a whole family of particles called hadrons. When the muon's cloud flickers into quarks and the gluons that glue them, you get the hadronic contribution. It is far larger than the weak piece and far harder to calculate than either of the others, because the strong force does not allow the neat term-by-term approach that worked so beautifully for light. That difficulty is not a failure of effort. It is built into the strong force itself. the electromagnetic force is weak enough that you can compute its effects as a series of smaller and smaller corrections, the way Schwinger and Kinoshita did. The strong force is too strong for that trick. Near the energies that matter for the muon, its corrections do not shrink politely. They pile up, and the clean ladder of diagrams collapses. You need a different way to get the number, and there is no single agreed road. So the muon's predicted anomaly is a sum of 3 terms with 3 very different personalities. The electromagnetic term is huge and exact. The weak term is small and solid. The hadronic term is medium-sized and for decades the least certain number in the whole calculation. When physicists quote an uncertainty on the muon prediction, that uncertainty is almost entirely the hadronic piece. Everything else is nailed down. This is the map you need for the rest of the journey. The entire anomaly, the famous gap between prediction and measurement, is smaller than the uncertainty that once hung over the hadronic term. That means the gap was always entangled with how well we could compute the strong force's whisper. To see how the anomaly was born and how it vanished, we have to walk into each of these 3 terms in turn, starting with the one physicists can hold most firmly, the towering electromagnetic mountain that Toichiro Kinoshita spent a lifetime climbing. Start with the easy piece, the one physicists trust most, and notice that even the easy piece is a monument of labour. The electromagnetic contribution to the muon's anomaly is the same kind of calculation Schwinger did, just carried much, much further. It is the sum over every way the muon's cloud can flicker using only photons and charged particles, drawn as Feynman diagrams and added up, term after term, deeper and deeper into the froth. The first term is Schwinger's, a single loop, one virtual flicker, the fine structure constant over 2 pi. The next level allows 2 flickers at once, and already there are several diagrams to draw and evaluate, each a small integral to be solved. The level after that, 3 flickers, brings dozens. The level after that brings hundreds. Each new layer of the cloud multiplies the work, because there are simply more ways for several virtual events to happen together. By the time you reach the 5th layer, where 5 separate virtual events occur at once, the count has exploded into the thousands. The full set at that level runs to more than 10,000 distinct diagrams. Each one stands for a specific, tangled way the vacuum can froth around the muon, and each must be turned into a precise number. No person could draw, let alone solve, 10,000 such integrals by hand. The calculation became a problem for computers as much as for physicists. The person most bound to this effort was Toichiro Kinoshita, a Japanese-born physicist who worked for decades at Cornell University. He was patient and relentless, the kind of scientist who would chase a calculation across years rather than leave it unfinished. With his collaborators, he built the computer methods needed to generate the diagrams, evaluate the enormous integrals, and check the results against each other. He carried the muon's electromagnetic anomaly out to the 5th layer and beyond, a feat that took much of a working life. The payoff is precision that feels almost unfair. The electromagnetic piece of the muon's anomaly is now known to more decimal places than the experiment can yet test. It rests on the same physics that made the electron's prediction match measurement to 1 trillion parts, so we have every reason to trust it. When physicists say the muon prediction is uncertain, they are emphatically not talking about this term. The electromagnetic mountain has been climbed, surveyed, and mapped to the summit. It helps to hold the sizes in mind. Almost the entire anomaly, the bulk of G-2/2 for the muon, comes from this electromagnetic piece. It is the dominant contribution by far, and it is the one we can compute most exactly. If the muon's wobble depended only on light and charged particles, the prediction and the measurement would simply agree, the way they do for the electron, and there would be no story to tell. But the muon is heavy, and its cloud is not so pure. Sitting on top of that towering, trustworthy electromagnetic number are 2 smaller contributions that the electron barely feels. They are smaller in size, but they carry nearly all the doubt. The famous anomaly lives not in the great mountain we can map, but in these smaller foothills we can only partly see. The smaller of the two foothills is the weak nuclear force, and although it is the tiniest piece in the whole sum, it is a beautiful one, because it shows the muon's wobble quietly registering the heaviest, rarest partners the standard model has to offer, including the famous Higgs. The weak nuclear force is the quiet engine behind certain kinds of radioactivity, the slow transformations that, among other things, let the sun shine by turning one kind of particle into another deep in its core. Unlike electromagnetism, which reaches across a room, the weak force acts only across distances far smaller than an atomic nucleus. Its reach is short because its carriers are heavy, and that heaviness is exactly what makes its mark on the muon so faint. 3 heavy particles carry the weak interaction's effects into the muon's cloud. 2 are the W and the Z, discovered at the European laboratory CERN in the early 1980s, each roughly 80 to 90 times the mass of a proton. The third is the Higgs, the particle tied to the field that gives many others their mass, found at CERN's Large Hadron Collider in 2012 after a search of nearly 50 years. All 3 are far heavier than the muon itself. By the rule we met earlier, heavy partners flicker into the cloud only rarely, so their contribution to the anomaly is small. The weak piece is the smallest of the 3 terms in the muon's prediction by a wide margin, a tiny correction far out in the decimals. If you pictured the whole anomaly as a tall building, the electromagnetic piece would be nearly all of it, and the weak piece would be a thin coat of paint near the very top. And yet that thin coat is one of the most satisfying things in the calculation. The muon is heavy enough that its wobble genuinely feels the W, the Z, and the Higgs flickering around it, even though they vanish almost instantly. Measure the muon precisely enough, and you are, in a real sense, detecting the presence of these massive particles indirectly, through the faint trace they leave on a smaller particle's magnetism. The wobble knows the Higgs is there. The weak contribution is also delicate to compute, but it is under good control. It involves only a handful of well-understood particles whose masses and behaviours have been measured directly in colliders. There is no wild, uncontrolled froth here. Theorists can calculate the weak piece carefully and pin down its small value with confidence. Like the electromagnetic mountain, the weak whisper is trustworthy. It is small, but it is not in doubt. So far, the muon's prediction is in excellent shape. The electromagnetic piece is enormous and exact. The weak piece is tiny and solid. 2 of the 3 terms are firmly nailed down, computed from particles we understand and have seen with our own detectors. If those were the only contributions, the muon's predicted anomaly would be as sharp as the electrons, and any disagreement with experiment would point cleanly and immediately at something new. But there is the 3rd term, and it sits between the other 2 in size while towering over them in difficulty. It comes from the strong nuclear force, the force that binds quarks together inside protons and the wider family of hadrons. This hadronic contribution is much larger than the weak whisper, and far less certain than either of the clean pieces. Nearly all the uncertainty in the entire muon prediction lives right here. That is the crucial point to carry forward. The gap between prediction and measurement, the anomaly that kept physicists awake, was always about the same size as the wobble in this one hard term. So the whole question of whether the anomaly was real, or merely a sign that we could not yet compute the strong force well enough, comes down to how accurately we can pin down the hadronic piece. To see why it is so hard, we have to look at what the strong force actually does, and why it refuses to be tamed by the tidy ladder of diagrams. The strong nuclear force has a personality unlike anything else in physics, and understanding that personality is the key to the whole anomaly. It is the force that holds quarks together inside a proton, and it is carried by particles called gluons. Its defining trait is that, instead of weakening as you try to pull 2 quarks apart, it grows stronger, like a stretching rubber band that pulls back harder the further you stretch it. Quarks are never found alone. They are forever bound into hadrons like the proton, the neutron, and a large family of heavier cousins. This is why the tidy approach that conquered electromagnetism fails here. For light and charged particles, the force is weak enough that each successive layer of the cloud contributes less than the one before, so the sum of diagrams settles down to an answer. Schwinger's term dominates, the next is smaller, the next smaller still. The series behaves. With the strong force at the energies that matter for the muon, the layers do not shrink. The corrections pile up rather than fade, and the orderly ladder of diagrams simply collapses. So when the muon's cloud flickers into quarks and gluons, theorists cannot just draw a few pictures and add them up. The quarks immediately bind themselves into a swarm of hadrons, tangled together by the relentless strong force, and there is no clean, term-by-term way to compute what that swarm contributes to the wobble. This hadronic contribution is medium-sized, far larger than the weak whisper, and it is the single most uncertain number in the entire prediction. It splits into two parts, and it is worth naming them because they return later. The larger part is called hadronic vacuum polarization. Picture the muon's photon briefly turning into a churning blob of quarks and gluons before turning back, a hadronic bubble in the cloud. This is the dominant strong force effect on the wobble, and the dominant source of doubt. The smaller part, called hadronic light by light, involves light scattering off light through a hadronic haze, and it is even harder to picture, though smaller in size. For decades, the hadronic vacuum polarization piece was the wall that blocked progress. Everyone agreed it mattered most. No one could compute it from pure theory the way they computed the electromagnetic piece, because the strong force would not cooperate. The accuracy of the whole muon prediction was hostage to this one churning hadronic blob, and to whatever method physicists could find to measure or simulate it. Here is the honest shape of the problem. The famous anomaly, the gap between the muon's measured wobble and its predicted wobble, was always roughly the same size as the uncertainty hanging over this hadronic term. That means the gap and the doubt were tangled from the start. If the hadronic blob contributed a little more than thought, the prediction would rise to meet the measurement and the anomaly would shrink. If it contributed a little less, the gap would stand and look like new physics. So the entire 20-year drama hinges on one quiet question. How much exactly does the churning hadronic blob add to the muon's magnetism? Everything else in the prediction is solid. This is the loose stone, and the anomaly was always balanced on top of it. Physicists found not one way to pin down the blob, but two, built on completely different foundations. One reads the answer out of real collisions in particle accelerators. The other simulates the strong force directly on a computer. For years, the two roads agreed, then they split, and that split is where the resolution of the anomaly was eventually found. We turn first to the older road, the one that reads the vacuum's froth out of collisions that actually happened. The first way to pin down the churning hadronic blob is to refuse to calculate it from theory at all, and instead to measure it. The reasoning is elegant. That same blob of quarks and gluons, the one that flickers in the muon's cloud, can also be made for real in a particle collider. If you smash an electron into its antimatter twin, a positron, the two annihilate into a pulse of pure energy, and that energy can turn into a spray of hadrons. The very process that haunts the muon's wobble can be staged and watched directly. So physicists at collider laboratories around the world spent decades carefully measuring how often electron-positron crashes turn into hadrons across a wide range of collision energies. They compared that to how often the same crashes produce a simple pair of muons, a process they understand perfectly. The ratio of those two rates is called the R ratio, and it is in effect a direct readout of how eagerly the vacuum produces hadrons at each energy. It is the froth measured. With the R ratio in hand, there is a known mathematical recipe to turn it into the hadronic contribution to the muon's anomaly. You weight the measured collision rates by a particular factor and add them up across all energies. The strong force never has to be calculated from scratch. Nature does the hard part inside the collider, and you simply tally the results. This data-driven method was, for a long time, the gold standard for the hardest term in the prediction. Many experiments contributed pieces of this measurement over the years at laboratories in Italy, the United States, China, and Russia, each covering different collision energies with different detectors. Names like KLOE in Italy and Babar in California became familiar in this corner of physics. Their results were combined painstakingly into a single best estimate of the hadronic blob, with an uncertainty small enough to make a real prediction for the muon. When theorists assembled the full prediction this way, with the electromagnetic mountain, the weak whisper, and the data-driven hadronic blob, they got a specific number for the muon's anomaly. Set that beside the measured wobble, and the two did not quite match. The measurement sat a little higher than the prediction, by an amount close to the combined uncertainty. That small, persistent excess is the anomaly, and through the data-driven method it looked real and stable for years. In 2020, a large group of theorists pooled their work into a single agreed prediction, often called the Theory Initiative White Paper, built on this data-driven approach. It became the official line in the sand. When the muon's wobble was finally measured with new precision, this is the number it would be compared against. And compared against it, the measurement stood meaningfully above the prediction, opening the gap that made headlines and kept people awake. For a while, this looked like the story's climax in the making. The clean pieces of the prediction were trusted. The hadronic blob had been measured, not guessed, through millions of real collisions. If the muon still came out high, the natural conclusion was that something beyond the standard model was flickering in its cloud, some new and undiscovered particle adding its weight to the wobble. But measuring the blob through collisions is not the only road. A second, completely independent method had been growing in power for years, one that does not measure the strong force at all, but simulates it directly, building the churning blob inside a computer from the bare laws of quarks and gluons. That method was about to give a different answer. The second road to the hadronic blob does something that sounds impossible. Instead of measuring the strong force in a collider, it computes it directly from the fundamental equations of quarks and gluons, the theory called quantum chromodynamics. The trouble, as we saw, is that the strong force defeats the usual ladder of diagrams, so physicists reached for a different tool entirely, one built not on pencil and paper series, but on raw computational force. The method is called lattice quantum chromodynamics, lattice QCD for short. The central idea is to give up on smooth, continuous space and time, and replace them with a grid. Imagine chopping a small region of space-time into a fine three-dimensional mesh of points, like the corners of a vast stack of tiny boxes, with time as another axis. On this lattice, the equations of the strong force become a problem a computer can attack directly, point by point, without needing the force to be weak. You're not approximating the froth with a series, you're simulating it. The cost is enormous. To capture the churning blob accurately, the lattice must be fine enough to resolve the small-scale structure of quarks and gluons, and large enough to hold a whole hadron, all at once. The number of points grows ferociously, and the computation devours time on the largest supercomputers in the world. For years, lattice calculations of the muon's hadronic blob were too rough to compete with the precise data-driven number from collisions. The grid simply could not be made fine enough. That changed over the last decade as both computers and methods improved. Several independent teams around the world took up the challenge. Groups known by initials like RBC and UKQCD, the Mainz collaboration, the Extended Twisted Mass collaboration, and others, each building the blob on its own lattice with its own techniques. The fact that there were several independent groups mattered enormously, because it meant the answer could be cross-checked rather than trusted on faith. The reason this second road is so valuable is that it shares almost nothing with the first. The collider method relies on real measurements and a recipe to convert them. The lattice method relies on pure theory and brute computation, with no collision data fed in at all. If two methods built on completely different foundations agree, you can be confident the answer is right. If they disagree, then one of them is missing something, and the disagreement itself becomes a clue worth chasing. For most of the muon story, the lattice was not precise enough to say much. The data-driven number ruled, and it gave the anomaly its apparent reality. But as the lattice calculations sharpened, they began to produce numbers precise enough to set beside the collider result for the first time. The stage was set for a direct comparison between the two roads to the hadronic blob, the measured and the simulated. When that comparison finally came, it did not go as expected. The simulated blob came out larger than the measured one. A larger hadronic contribution means a larger predicted anomaly, which means the prediction rises toward the measurement and the gap shrinks. If the lattice was right, the muon might not be anomalous at all. The famous excess might simply be the data-driven blob coming out a little too small. That tension between the two ways of pinning down the strong forces whisper is the real heart of the resolution we're building toward. But before we can follow how it played out, we need to understand the other half of the story, the experiment itself, and the genuinely clever trick that lets physicists measure the muon's wobble so precisely in the first place. It begins with a decision not to measure the magnet's full strength at all, but only the tiny excess past 2. To measure the muon's magnetism, you might think the obvious plan is to measure the full strength of its little magnet, the whole G-factor, as precisely as possible. But the full G-factor is close to 2, and the interesting physics, the anomaly, lives only in the tiny excess past 2. Measuring the whole thing and then subtracting 2 would mean chasing a small difference between two large numbers, where tiny errors in the large numbers swamp the small result you actually want. The experiment's central stroke of genius is to skip the large number entirely and measure the excess directly. The trick rests on a difference between two kinds of motion. When you send a muon circling around a ring inside a magnetic field, two things turn at once. The muon's path turns, sweeping it around the ring, and the muon's spin, its little magnetic axis, also turns. The question is whether those two turnings keep perfect step. If the muon's G-factor were exactly 2, as Dirac's clean equation says, the spin would turn at precisely the same rate as the path. The little magnetic arrow would point the same way relative to the direction of travel on every lap, like a car whose steering wheel rotates exactly in time with the road. There would be no drift, no relative wobble, nothing extra to see. The spin and the motion would be locked together forever. But the G-factor is not exactly 2. It is 2 plus the tiny anomaly. That sliver of extra magnetism makes the spin turn just slightly faster than the path. With each lap around the ring, the muon's magnetic arrow creeps a little further ahead of its direction of motion. Over many laps, that creep adds up into a slow, steady rotation of the spin relative to the velocity. This slow extra rotation is the anomalous precession, and its rate depends only on the excess past 2. This is the quantity the experiment measures, not the whole G-factor, but the rate of that slow creep, the speed at which the spin pulls ahead of the motion. That creep rate is directly proportional to the anomaly itself, the G-2/2 we have been chasing since Schwinger. By measuring the creep, physicists read the sliver straight off, never having to measure the large number 2 at all. The hardest part of the problem is sidestepped by design. It is worth pausing on how clever this is. The experiment is built around a deliberate choice to be blind to the boring part and sensitive only to the interesting part. It is like a clock built to ignore the hour hand and report only the slow drift of a second hand running a hair fast. By caring only about the drift, the apparatus throws its entire precision at the one number that carries the physics and wastes none of it on the value everyone already knows. To make the creep measurable, you need a great many muons, all with their spins pointing the same way to start, circling in a very uniform magnetic field for as long as their short lives allow. You need to know the strength of that field with extreme care, because the creep rate depends on it, and you need a way to read out, lap after lap, which direction each muon's spin is pointing, so you can watch the slow rotation build up. Each of those needs shaped the real machine. That machine is a great ring of magnet 50 feet across, and the way it turns dying muons into a readable rhythm of their own decay is the next piece of the story. It also depends on one more subtle trick, a special muon speed chosen so that the electric fields used to hold the beam in place do not spoil the delicate measurement of the creep. There is a problem with circling muons that nearly ruins the whole measurement, and the way around it is one of the prettiest tricks in experimental physics. A magnetic field alone can bend the muons into a circle, but it cannot keep them from drifting up and down, slowly spreading out of the ring. To hold the beam in a tight loop, the experiment needs to squeeze it vertically, and the natural tool for squeezing charged particles is an electric field. Here is the trouble. The slow creep of the muon's spin, the very thing being measured, responds not only to the magnetic field, but also to any electric field the muon passes through. Add electric fields to focus the beam, and you risk nudging the spin's creep by an unknown amount, polluting the one number you care about. The cure for the beam's wandering threatens to corrupt the measurement itself. The escape is to choose the muon speed with great care. The electric field's effect on the spin's creep depends on how fast the muon is moving, and there is one special speed where that effect cancels out almost entirely. At that particular energy, the electric field still squeezes the beam and holds it in place, but its influence on the delicate creep of the spin shrinks to nearly nothing. The experiment can focus the muons without spoiling the measurement. That special speed is called the magic momentum. For muons, it sits at an energy of about 3 billion electron volts, which works out to muons moving at better than 99.9% of the speed of light. The experimenters tune their muon beam to that exact energy, so that every muon entering the ring travels at the magic momentum. It is a single, sharply chosen number that makes the entire precision measurement possible. It is worth sitting with how fortunate this is. There was no guarantee that such a convenient speed would exist at all. It falls out of the way the magnetic and electric effects on the spin happen to combine, a quirk of the underlying equations. Nature left a narrow window where you can both hold the beam and read the spin cleanly, and the muon's mass places that window at an energy the experiment can actually reach. The magic momentum is a gift the experiment was lucky to be handed. This single choice shapes almost everything about the machine. The ring must be sized so that muons at the magic momentum bend into exactly the right circle. The focusing fields must be set to squeeze that particular beam. And because muons at this energy are moving so close to light speed, Einstein's time dilation stretches their fleeting lifetime as seen from the lab, giving each muon more laps before it decays. The faster they go, the longer the lab gets to watch them. Even stretched by relativity, though, the muons do not last long. A muon at the magic momentum survives for only a few tens of millionths of a second in the laboratory's frame, enough for a few hundred laps around the ring before it falls apart. That is a brutally short window in which to watch the slow creep of the spin build up. The experiment has to extract its precision from a swarm of particles that are, all of them, in the act of dying. So the design has quietly committed to a race. Inject a tight bunch of muons at the magic momentum, all spinning the same way, and watch their spins creep ahead of their motion for the few hundred laps before they vanish. The faster you can read each muon's spin direction, and the more muons you can pour through, the sharper your measurement of the creep, and so of the anomaly. That raises the final practical question. How do you tell, from outside the ring, which way a given muon's spin is pointing as it races past at nearly the speed of light? The answer turns the muon's own death into a signal, using the strange way that a dying muon throws out its decay products. The muon hands the experiment a gift when it dies. When a muon decays, it does not throw out its decay electron in a random direction. Because of the way the weak nuclear force works, the muon preferentially flings that electron in the direction its spin is pointing. The dying muon, in effect, points the way it was facing as it goes. This is the quiet fact that makes the whole measurement readable. So the experiment surrounds the ring with detectors that catch the electrons thrown off by decaying muons. The muons themselves are invisible as they circle, but each decay sends an electron outward, and the direction of that electron carries the memory of where the muon's spin was pointing at that instant. By collecting millions upon millions of these decay electrons, the experiment can reconstruct moment by moment where the muon's spins were aimed. Now bring back the slow creep. As the muons circle, their spins rotate slowly ahead of their motion, the anomalous precession. That means the direction in which they preferentially fling their decay electrons also rotates slowly. At one moment the spins point outward and the detectors catch a flood of electrons. A little later the spins have crept around to point inward and the detectors catch fewer. The count of detected electrons rises and falls in step with the creeping spin. Plot the number of detected electrons against time, and you get one of the most famous pictures in modern physics. It is a curve that falls away steadily, because the muons are dying off, and there are fewer of them as time passes. But riding on top of that fall is a clear, regular ripple, a wiggle, as the spins creep around and the electron count swings up and down. Physicists simply call it the wiggle plot, and its rhythm is the anomaly made visible. The whole measurement reduces to reading that wiggle. The rate of the ripple, how many times it swings up and down each second, is the rate of the spin's creep, which is directly proportional to the anomaly. Count the wiggles precisely, measure the magnetic field that drives them with equal care, and you have measured G-2/2 for the muon. The dying particles have written the answer into the rhythm of their own decay. To pin the wiggles rate down to many decimal places, you need staggering numbers of muons. A single muon's decay tells you almost nothing. Only when you stack up the electrons from billions of decays does the smooth wiggle emerge cleanly from the noise, sharp enough to measure its rate with great precision. The experiment runs for years, pouring bunch after bunch of muons into the ring, building the wiggle plot from an immense pile of individual deaths. Alongside the wiggle, the experiment must measure the magnetic field threading the ring with matching care, because the creep rate depends on both. Physicists map the field throughout the ring using finely tuned probes, knowing it to a few parts in a billion. The final anomaly comes from combining two extraordinarily precise measurements, the rate of the wiggle and the strength of the field, into the single number that theory has been straining to predict. This is the method that turns a dying, invisible particle into the sharpest probe of the vacuum we have. A tight bunch of muons at the magic momentum, a uniform field mapped to a sliver, detectors counting the decay electrons, and a wiggle plot whose rhythm reveals the anomaly. The technique was not invented all at once. It was first carried to real precision at a laboratory on Long Island, in an experiment whose hint of an anomaly first made physicists lose sleep. The first place this technique reached truly fearsome precision was Brookhaven National Laboratory on Long Island in New York. Through the late 1990s and into 2001, an experiment there known by its codename E821 sent muons circling through a great superconducting ring 50 feet across and read the wiggle in their dying. It was the most precise measurement of the muon's anomaly the world had yet seen. When the Brookhaven team finished and compared their measured anomaly to the best theoretical prediction of the time, the two numbers did not match. The measurement sat above the prediction. The gap was small, but it was larger than the combined uncertainty of measurement and theory by a meaningful margin. In the language physicists use to judge such things, the disagreement stood at roughly 3 standard deviations, 3 sigma, from 0. That phrase deserves a plain handle. When physicists say a result is 3 sigma, they mean the gap is about 3 times the size of the expected wobble in the numbers, so it is unlikely, though not impossible, to be a fluke of chance. By convention, 3 sigma is called evidence, something worth taking seriously, while 5 sigma is the higher bar required to claim a true discovery. Brookhaven's anomaly sat in the uncomfortable middle, too large to dismiss and too small to celebrate. So the result hung there, tantalizing and unresolved. The muon's measured wobble was a hair larger than the standard model seemed to predict, exactly the kind of small excess that a new, undiscovered particle flickering in the muon's cloud might produce. If real, it would be the first crack in the standard model found by this method, a direct hint that the inventory of nature was incomplete. If not real, it was either a subtle flaw in the experiment or a shortfall in the hard hadronic calculation. This is the moment the anomaly began to keep physicists awake. A 3 sigma gap is precisely the kind of result that will not let you rest. It is strong enough that you cannot ignore it, and weak enough that you cannot trust it. Theorists pored over the hadronic blob, wondering if the strong force piece had been slightly underestimated. Experimenters scrutinized every part of the Brookhaven apparatus, hunting for any overlooked effect that might fake an excess. The honest conclusion was that Brookhaven alone could not settle it. The experiment had reached the limit of what its Muon beam and its running time allowed. To know whether the gap was a discovery or a mirage, someone would have to measure the Muon's anomaly again, with more muons, a cleaner beam, and even greater precision, and see whether the same small excess appeared. The Brookhaven result was a question mark drawn very sharply, but still a question mark. There was a complication that kept hope and doubt evenly balanced. The size of the gap depended on the theoretical prediction, and that prediction leaned on the uncertain hadronic blob. So the 3 sigma anomaly was never purely an experimental fact. It was the distance between a precise measurement and a prediction whose hardest piece carried real doubt. Closing in on the truth would require sharpening both sides at once, the measurement and the calculation. The experimental side moved first, and it moved in a way that became legendary. The Brookhaven ring, that 50-foot superconducting magnet, was the heart of the apparatus and far too valuable to abandon. Rather than build a new one, physicists decided to move the existing ring to a laboratory near Chicago that could feed it a far purer, more intense beam of muons. The trouble was that the ring could not be taken apart. It would have to travel in one piece across half a continent. The ring at the heart of the experiment is a single circle of magnet 50 feet across, holding delicate superconducting coils that cannot be bent or twisted more than a few degrees without ruining them. It was built at Brookhaven in the 1990s, and when physicists decided to continue the hunt at Fermilab, the great accelerator laboratory in Batavia, Illinois, near Chicago, they faced a daunting fact. Building a new ring would cost roughly 10 times as much as moving the old one, so they chose to move it. The catch was that the ring could not be disassembled. Most of the experiment could be packed into trucks, but the great magnetic ring had to travel whole, kept nearly flat the entire way, or its inner wiring would be wrecked beyond repair. The team faced the problem of carrying a fragile 50-foot circle, weighing many tons, across more than 3,000 miles of the United States without letting it tilt. It was as much a feat of moving as of physics. They considered hauling it overland the whole way, and even briefly entertained a helicopter, before settling on a route mostly by water. In the summer of 2013, the ring was rolled slowly out of its building at Brookhaven on a specially built support and carried across the laboratory grounds to a marina on Long Island's South Shore. There it was loaded onto a barge. The plan was to send it by sea around the coast and up through the rivers of the American interior. The barge carried the ring down the Atlantic coast, around the tip of Florida, into the Gulf of Mexico, and up a series of rivers toward Illinois, a long, patient voyage by water that avoided the jolts of the road. Then, near Chicago, the ring was lifted back onto a custom truck and driven the last stretch over 3 nights, moving at a walking pace with police closing the highways ahead of it. The whole journey covered about 3,200 miles and took 35 days. What happened along the way surprised everyone. The slow-moving ring became a kind of travelling spectacle. People followed its progress online, came out to watch it pass, and gathered to greet it. When it finally rolled onto the Fermilab site in the small hours of a July morning, a crowd was waiting, and a celebration followed the next day with thousands on hand. A piece of fragile scientific apparatus had quietly become something the public felt invested in. It is worth dwelling on this human detail, because the popular telling of the Muon story often skips it for the physics. The most precise probe of the quantum vacuum we possess had to be floated on a barge past the Florida coast, and trucked through sleeping suburbs at 10 miles an hour, with engineers watching anxiously to be sure it never tilted too far. The grand and the mundane sat side by side. The deepest question in physics rode across the country on a boat. The reason for all this effort was simple. Fermilab could give the ring something Brookhaven could not: a purer and more intense beam of muons. A cleaner beam means fewer stray particles to confuse the measurement, and more muons to build a sharper wiggle plot. With the same trusted ring fed by a better beam, physicists hoped to measure the muon's anomaly several times more precisely than Brookhaven had. Precisely enough to say whether the 3 sigma hint was real. Once the ring reached Fermilab, it had to be carefully reassembled, cooled back down, and coaxed to produce the same exquisitely uniform magnetic field it had before the trip. That took years of patient work. By the time the field was ready and the new beam was running, the stage was set for the experiment that would either confirm the old anomaly or make it vanish, this time with the cleaner muons that only Fermilab could provide. At Fermilab, the ring was given a fresh purpose and a far better supply of muons. Fermilab's accelerators can produce one of the most intense and well-controlled beams of muons in the world, and crucially a cleaner one, with fewer of the stray contaminating particles that had complicated the work at Brookhaven. After the long journey and years of careful reassembly, the magnet was cooled, its field tuned to extraordinary uniformity, and the new experiment named E989 began to circle muons once more. The plan was straightforward in aim and brutal in execution. Do exactly what Brookhaven had done, but better, with more muons, a cleaner beam, and tighter control over every source of error, until the measured anomaly was several times more precise. If the small excess seen at Brookhaven was real, it should reappear, now sharpened, standing out more clearly from the uncertainty. If it was a fluke or a flaw, the better measurement should soften it or wash it away. Precision at this level is not won by any single clever step. It is won by hunting down dozens of tiny effects that could each shift the answer by a sliver and controlling everyone. The team had to map the magnetic field throughout the ring to a few parts in a billion, account for the slow drift of muons within the beam, correct for the way the field varied in time and place, and understand their detectors well enough to trust the wiggle they read. Each correction was a small research project of its own. The muons were injected into the ring in tight bunches, all spinning the same way, and the detectors counted the electrons from their decays, building the familiar wiggle plot from billions of individual deaths. Over several years of running, bunch after bunch, the experiment accumulated an enormous pile of data, far more than Brookhaven had managed. With each year of running, the wiggle grew sharper and the measured anomaly more precise. But the team faced a subtler danger than any magnetic drift, a human one. When you already know what answer you're hoping for, it is dangerously easy, without meaning to nudge your analysis toward it, to treat a result that confirms your hope a little more gently than one that does not. The Brookhaven anomaly was famous. Everyone working at Fermilab knew the number they were chasing, and what it would mean to confirm it. That knowledge was itself a threat to the measurement. So the experiment was built to protect the physicists from their own hopes. The exact answer was hidden from the people analysing it, deliberately until the very end. They could refine their methods, hunt their errors, and check their work in every way, all without being able to see the final number they were converging on. Only when the analysis was completely finished and frozen would the true value be revealed, and not before. This deliberate self-blinding is one of the quiet glories of modern physics, and it deserves a closer look, because it is exactly how a field guards itself against wishful thinking. The Fermilab team did not simply promise to be careful. They engineered their own ignorance, locking the crucial number away behind a secret offset so that no amount of unconscious bias could steer them toward the result they wanted to find. The method was almost theatrical in its caution. A frequency that the entire measurement depended on was shifted by a secret amount, a number known to no one on the analysis team, sealed away until the work was done. The physicists spent years measuring the muon's wobble without being allowed to know what their own apparatus was actually saying. To see how that secret was kept and how it was finally opened, we turn to the practice of blinding itself. Blinding is the practice of hiding the answer from yourself on purpose, and at Fermilab it was carried out with great care. The whole measurement of the anomaly depended on comparing two frequencies, the rate of the wiggle and the strength of the magnetic field. The team arranged for the clock that timed the wiggle to be deliberately set to the wrong rate, offset by a secret amount that none of the analysts knew. Every number they computed would therefore be shifted away from the truth by an unknown sliver. The secret offset was not casually chosen or loosely held. It was set by a small number of people outside the main analysis, written down and locked away, in one telling a slip of paper sealed in an envelope and kept in a safe. The physicists doing the analysis could work for years with their shifted numbers, refining everything, without any way to know how their results compared to Brookhaven's famous value or to the theoretical prediction. They were flying with the most important dial covered. The point of this is subtle but vital. With the answer hidden, there is no way for hope to creep into the analysis. A physicist deciding how to handle some small correction cannot be swayed, even unconsciously, by whether that choice nudges the result toward the anomaly they would love to confirm, because they cannot see which way any choice pushes the final number. Every decision has to be justified on its own merits, blind to its effect on the headline value. Only when the entire analysis was finished, checked and frozen, with every correction settled and no further changes allowed, was the secret offset revealed. In a kind of ceremony, the hidden number was read out and applied, shifting the team's blinded result to its true value all at once. Until that instant, no one in the room knew whether the muon would confirm the old anomaly or erase it. The unblinding is the moment the experiment finally tells you what it found. There is something deeply admirable in this, and worth saying plainly. The physicists did not trust themselves to be objective, and so they built a system that did not require them to be. They treated their own desire for a discovery as a source of error to be controlled, just like a drifting magnetic field. The blinding is an act of scientific humility engineered into the apparatus, a confession that even careful people want to find what they hope to find. It also raises the stakes of the unblinding to something almost unbearable. Years of work by hundreds of people, the long journey of the ring, the careful mapping of the field, all of it comes down to a single moment when the envelope is opened and the true number appears. There is no adjusting it afterward. Whatever the muon has been saying all along, blinded from view, is revealed in one stroke, and the team learns at last whether the anomaly is real. This is how a field keeps itself honest when the temptation to find something is greatest. The muon's anomaly was the most exciting hint in particle physics, the thing everyone wanted to confirm, which is exactly why the measurement had to be sealed away from its own makers until the end. The discipline of blinding is the reason we can take the eventual results seriously, whichever way they fell. So the world waited for the envelope to be opened. After years of running at Fermilab and a long blinded analysis, the team prepared to unblind their first result, the measurement built from their earliest year of data. When that secret offset was finally applied and the true number appeared, it would either confirm Brookhaven's tantalizing excess or begin to make it disappear. And in the spring of 2021, the answer was revealed to a watching world. In April of 2021, the Fermilab team unblinded and announced their first result, built from their earliest full year of data. The world was watching, because everyone understood the stakes. Either the muon would confirm Brookhaven's old anomaly with sharper precision, strengthening the case for new physics, or the cleaner Fermilab measurement would soften the excess and begin to wave it away. The envelope was opened, the secret offset applied, and the number appeared. It confirmed Brookhaven. The Fermilab measurement of the muon's anomaly landed right on top of the old Brookhaven value, almost perfectly consistent with it, and once again it sat above the standard model prediction of the 2020 Theory Initiative. Two independent experiments decades apart on different sites with different beams, now agreed that the muon's wobble was a hair larger than the prediction said it should be. The hint had not gone away, it had hardened. Combining the new Fermilab result with the old Brookhaven one, the gap between the measured anomaly and the data-driven prediction grew to about 4.2 standard deviations. That is a meaningful step up from Brookhaven's 3 sigma. 4.2 sigma is strong enough that a chance fluctuation is quite unlikely, strong enough to make headlines around the world proclaiming a possible crack in the standard model, though still short of the 5 sigma bar that physicists demand before calling something a discovery. The announcement made a genuine splash beyond physics. Newspapers carried it on their front pages. The story was irresistible, a tiny dying particle whose faint magnetic wobble might be revealing the existence of unknown forces or undiscovered particles flickering in the vacuum. For a moment the muon was famous, and the language of the coverage leaned hard toward discovery, toward the sense that physics stood on the edge of something new. The physicists themselves were more careful, and their caution is the important part. They knew that the 4.2 sigma gap was the distance between a very precise measurement and a prediction whose hardest piece, the hadronic blob, was still genuinely uncertain. The experiment had done its job beautifully, but the prediction it was being compared against rested on the data-driven hadronic number, and that number had just been thrown into question by the rival lattice calculations. This is the knot at the centre of the whole story. The same year that lattice computers were beginning to suggest the hadronic blob might be larger than the collider data implied, the experiment confirmed the muon sitting high above the data-driven prediction. If the lattice was right and the blob was indeed larger, the prediction should rise, the gap should shrink, and the anomaly might not be new physics at all, but a sign that the data-driven blob had come out slightly too small. So the 2021 result, for all its drama, did not actually settle the question. It settled half of it. It proved that the muon's measured wobble was solid and reproducible, confirmed now by 2 experiments. What it could not prove was whether that wobble disagreed with nature, because nature's prediction depended on a hadronic number that 2 different methods could not agree on. The measurement was sharp. The target it was aimed at had gone blurry. The path forward was clear in principle. Sharpen the measurement further, with more years of Fermilab data, and at the same time resolve the dispute over the hadronic blob, between the collider-based number and the lattice-based one. The experiment was already well along on the first task, with far more data waiting to be analysed. The second task, settling the strong force calculation, was about to become the true battleground, and it was on the theory side that the anomaly would ultimately live or die. Fermilab kept running and kept analysing, and in 2023 the team released a second result built from far more data than the first. This measurement was substantially more precise than the 2021 announcement, with the uncertainty on the muon's anomaly cut down considerably. The experiment was steadily approaching the precision it had been designed to reach, tightening its grip on the muon's wobble year by year. The 2023 result agreed beautifully with the earlier one. The muon's anomaly came out at essentially the same value, now measured more sharply, with the experimental uncertainty reaching around 0.2 of a part per million. 3 measurements, Brookhaven and 2 from Fermilab, all pointed to the same number for the muon's wobble. On the experimental side, there was no longer any serious doubt about what the muon was doing. Its anomaly was known, and known well. With the measurement this solid, attention turned almost entirely to the prediction. The experimental wobble was nailed down. Whether it counted as an anomaly depended completely on what value the standard model said it should have, and that value was now openly contested. The clean pieces, electromagnetic and weak, were not in question. The whole argument had narrowed to the hadronic blob and to the standoff between the 2 ways of computing it. On one side stood the data-driven number, built from decades of collider measurements of electron-positron crashes into hadrons, the R-ratio method. It gave a smaller hadronic blob, which meant a lower prediction, which left the muon sitting high above it at 4+ sigma. This was the number behind the dramatic headlines. On the other side stood the lattice calculations simulating the strong force on a grid, which gave a larger blob, a higher prediction, and a gap with the muon that nearly vanished. These two could not both be right, and the difference between them was exactly the size of the famous anomaly. That is the uncomfortable fact that came into focus around 2023. The question was no longer really about the muon. The muon had spoken clearly. The question was about the strong force, and about why two respected methods for computing its contribution disagreed by just enough to make or break the most exciting result in particle physics. A natural worry was that one of the two methods harboured a hidden mistake. Perhaps the lattice simulations shared some subtle, systematic error that pushed them all too high, or perhaps the collider data was missing something, some hadronic process that detectors had failed to fully catch, which would make the measured R ratio come out too low. Both possibilities were taken seriously, and both pointed to the same conclusion. The resolution would come from understanding the strong force better, not from the muon. The lattice camp had a powerful argument in its favour. When the first precise lattice result appeared, from the Budapest-Marseille-Wuppertal collaboration, it was a single calculation, and a lone result can always be doubted. But over the following years, several independent lattice groups, using different methods and different approximations, began to compute the same hadronic blob, and to agree with one another. A chorus is harder to dismiss than a single voice. So by 2023 the situation had a clear shape. A rock-solid measurement of the muon, a clean and trusted prediction, except for one stubborn term and two rival ways of computing that term, splitting almost exactly along the line that separated discovery from no discovery. The crack in physics looked real if you trusted the collider data, and looked imaginary if you trusted the lattice. To see which way it would fall, we have to go back to the calculation that started the split, the lattice result that first slid the prediction toward the measurement. The calculation that changed everything came from a collaboration named for three cities, Budapest, Marseille, and Wuppertal, where its leading members worked. The BMW collaboration, as everyone called it, had spent years developing the methods and amassing the computer power to simulate the hadronic blob on a lattice with unprecedented precision. Around 2020 and 2021, they published a result that landed in the muon world like a thrown stone, sending ripples that have not fully settled even now. Their lattice calculation of the hadronic vacuum polarization, the churning blob, came out larger than the data-driven number that the collider measurements had long supplied. Not wildly larger, but larger by an amount that mattered enormously, because the muon's whole anomaly was itself small. A larger blob means a larger hadronic contribution, which means a higher predicted anomaly for the muon. The BMW number pushed the prediction up toward the measured value, and in doing so it threatened to close the famous gap. If the BMW result was right, the consequence was stark. The standard model's prediction for the muon, recomputed with the larger lattice blob, came out close enough to the measured wobble that the anomaly nearly disappeared. The muon would not be a crack in physics after all. It would be one more triumphant confirmation of the standard model, and the excess seen at Brookhaven and Fermilab would simply be the shadow of a hadronic blob that the collider method had estimated a touch too small. This was an unwelcome thought for many. The anomaly had been a beacon of hope, the brightest hint that new particles or forces lay just out of reach. The BMW calculation suggested the beacon might be a mirage created by an imperfect calculation of the strong force, not by anything new in nature. Whole avenues of theoretical work built on explaining the muon excess with hypothetical new particles suddenly rested on shakier ground. But the BMW result created a new puzzle even as it threatened to dissolve the old one. Its larger blob disagreed not only with the size of the muon anomaly, but directly with the data-driven number from collisions. The collider measurements of electron-positron crashes into hadrons gave a smaller blob. The lattice gave a larger one. Both could not be correct. The tension had been transferred. Instead of the muon disagreeing with theory, now two ways of computing theory's hardest piece disagreed with each other. A single lattice calculation, however careful, was not enough to overturn decades of collider data on its own. The natural and proper response was skepticism. Perhaps BMW had some subtle systematic error, some unaccounted for effect in their enormous simulation that pushed the answer high. The result was striking and important, but science does not pivot on one calculation, no matter how impressive. What it did, decisively, was reframe the question and demand a flood of new checks. So the BMW bombshell did not resolve the anomaly. It relocated it. It moved the disagreement from a clean comparison, the muon versus the standard model, into a murkier one, the lattice versus the collider data, where the answer depended on trusting one hard method over another. The path to resolution now ran through deciding which of the two ways of computing the hadronic blob deserved more trust, and that required a way to cross-check the lattice calculations against each other and against the data piece by piece. That cross-checking tool existed, and it became the decisive instrument of the whole affair. Rather than compare the full hadronic blob all at once, physicists found a way to slice it into pieces by the distances involved, and to compare just one well-behaved slice across every method. That slice, called the intermediate window, is where the lattice groups found their agreement and where the collider data was caught coming up short. Comparing the entire hadronic blob in one lump is treacherous, because different parts of it are sensitive to different things and carry different errors. So physicists devised a cleaner way to compare. They learned to slice the blob according to the distances, or equivalently the times, involved in the churning of quarks and gluons, separating the short distance part, the long distance part, and a middle slice in between. Each slice can be computed and compared on its own. The middle slice, called the intermediate window, turned out to be the perfect testing ground. It avoids the very short distances, where lattice simulations struggle with the fineness of their grid, and the very long distances, where they struggle with the size of their box. In that comfortable middle range, the lattice calculations are at their most reliable and precise, and several independent groups can compute the same well-defined quantity and check each other with real confidence. When the groups did this, the result was striking. For the intermediate window, the independent lattice collaborations agreed with one another closely. Groups using genuinely different methods all landing on the same value, with competing precision. This was the chorus that a single calculation could never provide. It is very hard to believe that several different teams, with different techniques and different sources of error, would all make the same mistake in the same direction by the same amount. Their agreement was powerful evidence that the lattice was getting the blob right. Then came the decisive comparison. The same intermediate window slice can also be built up from the collider data, from the measured R ratio. When physicists computed the intermediate window that way, from the collisions, it came out smaller than what the agreeing lattice groups found. The mismatch sat right in the cleanest, most trustworthy slice of the whole calculation, exactly where the lattice was most believable. The collider-based number in that window appeared to be falling short. This reframed the problem with great clarity. The disagreement was not some vague uncertainty smeared across the whole hadronic blob. It was concentrated in a specific, well-understood slice, where the lattice spoke with one confident voice, and the collider data disagreed with it. That sharp localization made the lattice case much stronger. If many independent simulations agree on a clean quantity, and the data does not, suspicion shifts toward the data, and toward whatever might be wrong with how the collisions were measured or assembled. The implication was uncomfortable for the data-driven method that had reigned for so long. If the collider-based R ratio was coming up short in the intermediate window, then perhaps the decades of electron-positron measurements were missing something. Or perhaps some of the experiments disagreed with each other in ways that had been averaged over too smoothly. The window comparison did not just favour the lattice. It pointed a finger at the collider data and asked hard questions of it. And there was a specific place to look. The hadronic blob is dominated by collisions that produce a particular pair of particles, two pions, in a certain range of energies. If the older collider measurements of that dominant process had come out slightly too low, it would explain everything: the shortfall in the window, the smaller data-driven blob, and the apparent anomaly. The whole question began to narrow onto a single, much-studied collision, and whether everyone had been measuring it correctly. That is exactly where a new and surprising measurement entered from an experiment in Russia. It measured that dominant Tupian process afresh, and it disagreed with the older collider data in just the direction the lattice and the window comparison suggested. The data-driven world, long thought settled, began to fracture from within, and the source of the anomaly came into sharper view than ever. The dominant piece of the hadronic blob comes from one particular outcome of electron-positron collisions, the production of a pair of pions, the lightest hadrons. Get that 2-pion process right, and you get most of the blob right. For years, several experiments had measured it, and their results had been combined into the standard data-driven number. Among the most precise were measurements from an experiment in Italy and another in California, and they broadly agreed with one another. Then, at the start of 2023, a measurement came from the CMD3 experiment at a laboratory in Novosibirsk, Russia. CMD3 measured the same Tupian process across the crucial range of energies with great care, and its result disagreed substantially with the earlier measurements. CMD3 found that the collisions produced pions somewhat more abundantly than the older experiments had reported. Its cross-section, the measure of how often the process happens, came out higher. A higher rate for the dominant process means a larger hadronic blob, and a larger blob, derived now from collider data itself, would push the data-driven prediction up, toward the lattice value and toward the measured muon, shrinking the anomaly. Remarkably, the CMD3 results sat much closer to the lattice calculations than to the other collider measurements. The newest and one of the most precise collision measurements was lining up with the lattice against the older collision data. This was a genuine shock to the data-driven method, because it meant the trouble was not simply lattice versus data, it was data versus data. The collider measurements of the single most important process no longer agreed among themselves. CMD3 stood apart from the Italian and Californian results by an amount far larger than their stated uncertainties allowed. Something was wrong somewhere in this web of experiments, and no one could yet say where. The honest state of things became this: the lattice calculations agreed with each other and pointed to a larger blob and a vanishing anomaly. The newest collider measurement, CMD3, agreed with the lattice, but the older, well-established collider measurements pointed to a smaller blob and a surviving anomaly, and they disagreed sharply with CMD3. The data-driven method, once the trusted gold standard, was now internally inconsistent and could no longer give a single confident answer. This is the kind of situation that physics finds genuinely difficult, and it is worth being plain about it. When two careful experiments measuring the same quantity disagree by more than their uncertainties, at least one of them has an error that has not been found. Resolving such a clash is slow, unglamorous work, rechecking calibrations, re-examining assumptions, looking for the subtle effect that one experiment handled differently from another. It cannot be rushed, and it had not been settled. But the overall weight of evidence had clearly shifted, with the lattice groups agreeing, the intermediate window favouring them, and now the newest collider measurement also agreeing with them. The larger hadronic blob looked increasingly likely to be the true one, and a larger blob meant a higher standard model prediction, one that rose to meet the muon's measured wobble. The anomaly was being squeezed from several directions at once, and the prediction was climbing toward the measurement. The people responsible for assembling the official standard model prediction now faced a hard choice. The community had been moving steadily toward the lattice value, supported by the window comparison and the CMD3 result, while the older data-driven number looked more and more isolated. When the theorists gathered to issue their updated consensus prediction in the spring of 2025, they would have to decide which evidence to trust, and their decision would determine whether the famous anomaly survived. The community that assembles the official standard model prediction is called the Muon G-2 Theory Initiative, a large international group of theorists who pool their work into a single agreed number with a single agreed uncertainty. They had issued their first consensus in 2020, built on the data-driven method, and that number was the line the muon had been measured against, the source of the famous 4.2 sigma gap. By 2025, that line no longer reflected what the field had learned. On the 27th of May, 2025, the Theory Initiative released a major update to its prediction. In the years between the two reports, the evidence had moved decisively. The lattice calculations had multiplied and converged, agreeing with each other across independent groups and methods. The intermediate window comparison had favoured them over the collider data, and the data-driven method had fractured internally, with CMD3 clashing with the older measurements and siding with the lattice. Faced with all this, the updated prediction leaned on the lattice calculations for the hadronic blob, rather than on the contested collider data. Because the lattice gave a larger blob, the new standard model prediction for the muon's anomaly came out higher than the 2020 value. It rose, in other words, toward the measured wobble. The prediction and the measurement, which had stood apart for so long, were brought into close agreement by this single change in how the hardest term was computed. With the higher prediction in place, the famous gap shrank dramatically. The disagreement between the muon's measured anomaly and the updated standard model prediction fell from the dramatic 4+ sigma of a few years earlier to something small within the combined uncertainties of theory and experiment. By the reckoning that followed, the tension dropped to roughly half a standard deviation, a level at which there is no meaningful disagreement at all. The anomaly, as a clash between muon and theory, had effectively vanished. It is important to be honest about what this update was and was not. It was not the discovery of a new particle, nor a flaw found in the experiment. It was a reassessment of the prediction, a decision to trust the converging lattice calculations of the strong force over the older and now internally contradicted collider data. The anomaly disappeared from the theory side because the theoretical target moved up to meet a measurement that had never wavered. This is a subtler and, in its way, more interesting outcome than a simple discovery would have been. For 20 years, the muon's wobble had been measured beautifully and consistently. What changed was our ability to compute what that wobble should be, and in particular our handling of the one term the strong force makes so hard. The lattice method, once too crude to compete, had grown precise and trustworthy enough to redraw the prediction, and when it did, the crack closed. The Theory Initiative was careful, as good scientists are, to note that the work is not finished. The lattice result is now well supported, but the disagreement among the collider experiments remains genuinely unresolved, an open wound in the data that still needs healing. The prediction rests on a confident interpretation of current evidence, not on a closed case. The anomaly is gone for now, but the reasons it is gone are still being firmed up. So as of late May 2025, the prediction stood higher and the gap stood narrow. All that remained for the experimental side was its final word, the most precise measurement of the muon's anomaly it would ever make, built from all the data Fermilab had gathered over years of running. That measurement came just a week later, and it confirmed everything, sealing the picture of a muon that, at last, agreed with the standard model. A week after the updated prediction, on the 3rd of June 2025, the Fermilab team announced their final result. It was built from all 6 years of data the experiment had collected, the full harvest of the Great Ring's run, and it was the most precise measurement of the muon's anomaly ever made or likely to be made for many years. The experiment that had begun with a barge journey across a continent had reached its end. The number was extraordinary in its precision, pinning the muon's anomaly to about 1/10 of a part per million, a sharpness that even surpassed the experiment's own original design goal, and it agreed with everything that came before. The final value sat squarely on top of the earlier Fermilab results, and the old Brookhaven measurement. Across more than 2 decades and 2 laboratories, every measurement of the muon's wobble had told the same story, now told most sharply of all. What had changed was not the measurement, but its meaning. Set against the old data-driven prediction, this exquisite number would still have sat high, still have looked like a 4 sigma crack. But set against the updated prediction, built on the converging lattice calculations of the hadronic blob, it agreed. The most precise measurement in this corner of physics matched the best current prediction. The muon's wobble was exactly what the standard model, properly computed, said it should be. So the 2 announcements, a week apart, completed the picture together. The theory update moved the prediction up to meet the long-standing measurement. The final experimental result confirmed that measurement with unprecedented precision. Between them, they closed the gap that had stood since Brookhaven. The anomaly that kept physicists awake, the brightest hint of new physics in a generation, had quietly resolved into agreement. There was a real poignancy in the timing. For many physicists, the dream had been that this final, most precise measurement would confirm a genuine break from the standard model, opening a door to new particles and forces. Instead, the measurement was a triumph and the anomaly was gone, dissolved by a better understanding of the strong force a week before the experiment's grand finale. The standard model, that much tested and stubbornly successful theory, had held once again. It is worth honouring what the experiment achieved, regardless of how the anomaly fell. The Fermilab measurement stands as one of the most precise confrontations between theory and experiment ever performed, a number known to 1/10 of a part per million for a particle that lives 2/millionths of a second. Whether or not it found new physics, it pushed human precision to a place it had never been, and it will remain the reference value for a generation. And the standard model's victory is itself a kind of wonder. This theory, assembled piece by piece over the 20th century, predicted the magnetism of a dying particle, including the faint contributions of the Higgs and the churning of quarks bound by the strong force, and it matched a measurement of staggering precision. That a human theory can get such a thing right, to so many decimal places, is not a disappointment. It is one of the most remarkable facts about our world. But to say the anomaly disappeared is not quite to say the story is over. A measurement was confirmed and a prediction caught up to it, yet the reason the prediction could be trusted rests on choosing the lattice over a set of collider measurements that still disagree among themselves. The crack between muon and theory closed, but a new crack between experiment and experiment opened in its place. To understand honestly what disappeared, we have to look at what remains. So what exactly disappeared? It was not the muon's wobble, which was measured the same way for 20 years and never moved. It was the gap between that wobble and the prediction, and that gap closed because the prediction rose to meet the measurement. The anomaly vanished from the theory side. No new particle was caught, no flaw found in the experiment. The thing that changed was our ability to compute the contribution of the strong force. This is a different kind of ending than the one most people imagined. The popular hope had been for a discovery, a flash in a detector revealing something beyond the known particles. What actually happened was quieter, and in its own way, deeper. A calculation that had long been too crude grew precise enough to be trusted, and when it was trusted, the famous excess turned out to be an artifact of computing the hadronic blob a little too small. The crack was in the prediction all along, not in nature. But honesty requires naming what is still unsettled, because the resolution is not as clean as a single agreed number might suggest. The updated prediction trusts the lattice calculations of the hadronic blob. Those calculations agree with each other impressively, and they agree with the newest collider measurement, CMD3. Yet they disagree with a body of older, careful collider measurements that had long been the standard. Those older measurements have not been shown to be wrong. They simply disagree. So the tension did not so much vanish as move. For 20 years, the puzzle was the muon against the standard model. Now the puzzle is one set of experiments against another, the older electron-positron collision data against CMD3 in the lattice. That clash among measurements of the same 2P process is real and unresolved. At least one of those experiments has an error no one has yet found. The anomaly was traded for a different, more technical mystery. This matters because the conclusion that the muon agrees with the standard model rests on choosing the lattice in CMD3 over the older data. That choice is well motivated, supported by the agreement of independent lattice groups, and by the clean intermediate window comparison. It is the best reading of the evidence today, but it is a reading, not a closed case, and a careful physicist holds it as a strong and likely conclusion rather than an absolute certainty. There is also a quiet lesson here about how science actually resolves its puzzles, which is rarely as dramatic as the headlines hope. Often the answer is not a thrilling discovery but a hard, patient reckoning with a difficult calculation or a disagreement between instruments. The muon anomaly was undone not by a new force but by years of grinding work on the strong force, by faster computers, cleverer methods, and the slow convergence of independent teams. That too is how physics moves forward. None of this diminishes what was achieved. We now understand the muon's magnetism, including its hardest hadronic piece, better than ever before, and the standard model passed a test of extraordinary precision. The disappearance of the anomaly is not a failure, but a clarification. We learned that the excess was a measure of our own incomplete calculation, not a message from undiscovered nature, and learning that is genuine progress. Still, the open clash among the collider experiments is a loose thread that physicists cannot leave alone, and they are not leaving it alone. New experiments are already being built and run to settle the disagreement directly, to measure the hadronic contribution in fresh ways, and to test the muon's wobble with entirely different machines. The story of the muon is not closed, it has simply entered a new and more careful chapter, and there is real work still to do. The clash among the collider experiments will not resolve itself by argument, so physicists are building new ways to settle it. One of the most elegant is an experiment at the European laboratory CERN called Muon. Instead of measuring electron-positron collisions and summing them into the hadronic blob, Muon takes a completely fresh approach. It fires a beam of muons through thin layers of material and watches how they scatter off the electrons in the atoms, measuring the strong force contribution in an entirely independent way. The idea is that the hadronic blob subtly affects how a muon and an electron deflect each other, and by measuring that deflection with great care, Muon can extract the same hadronic contribution that the collider summation and the lattice both target, but through a different door. If Muon's number agrees with the lattice, it would powerfully confirm the larger blob and the vanishing anomaly. If it agrees with the older collider data instead, the puzzle would deepen. Either way, it offers a clean, independent verdict. On the experimental side of the muon's own wobble, a wholly new measurement is taking shape in Japan at a facility called J-Park. This experiment, sometimes labelled E34, aims to measure the muon's anomaly using a technique quite different from the Fermilab approach. Rather than relying on the magic momentum and a large ring, it plans to use muons brought nearly to rest and then reaccelerated in a controlled way, circling in a much smaller apparatus with entirely different sources of error. The value of the J-Park experiment lies precisely in that difference. The Fermilab and Brookhaven measurements, for all their agreement, share the same basic method, the same kind of ring, and the same magic momentum trick. If some subtle flaw lurked in that shared technique, all three could be wrong in the same way. A measurement built on a genuinely different method would test that possibility. If J-Park reproduces the Fermilab wobble using different tools, our confidence in the measured anomaly becomes nearly unshakable. Meanwhile, the lattice calculations continue to sharpen, and the theorists continue to scrutinize the conflicting collider data, looking for the hidden error that must lie in one experiment or another. The work is patient and technical, the kind that rarely makes headlines but steadily firms up what we know. Over the coming years, these independent efforts, Muon, J-Park, more lattice work and renewed scrutiny of the collision data, will either lock in the disappearance of the anomaly or reopen it. It is worth appreciating how much remains genuinely open even after the anomaly's apparent resolution. The current picture that the muon agrees with the standard model is the best reading of the evidence, but it rests on choices that future measurements will confirm or overturn. Physics has not declared the matter permanently closed. It has reached a confident interim conclusion and immediately set about testing it from every independent angle it can devise. That ongoing test is the honest state of the field, so the muon remains, as it has been for decades, one of the sharpest tools we have for probing the deep vacuum, and the instruments aimed at it are only growing more precise. Even though the famous anomaly has faded, the muon's magnetism is still a frontier, still capable of revealing something new if the next round of measurements turns up a fresh disagreement. The particle nobody ordered is still doing the most careful listening in physics, and that brings us back to where we began, to the tiny spinning magnet and the wobble we can feel echoed in a magnet on a door. We set out to understand how a crack in physics could simply disappear. We now have the answer, and we can say it plainly, and then step back to see what this whole long story has really been about. Return to the beginning, to the magnet held near the refrigerator door and the slow lean of a spinning top. We asked a simple question at the start. How does a crack in physics simply disappear? Now we can answer it in plain words. The crack was the gap between the muon's measured magnetism and the predicted value, and it disappeared because the prediction, once we learned to compute the strong force properly, rose up to meet the measurement that had been right all along. That is the honest answer to the title's promise. The anomaly that kept physicists awake did not vanish because someone discovered a new particle or caught an error in a great experiment. It vanished because a calculation got better. The churning hadronic blob, the contribution of the strong force to the muon's wobble, had been estimated a little too small, and when independent lattice simulations grew precise enough to fix it, the famous excess melted away into agreement. Step back and consider what that single number really is. The muon's anomaly, the G-2/2 we have followed from Schwinger's headstone to a barge off the Florida coast, is in the end a census of the vacuum. It records every kind of particle that flickers in the empty space around a muon, the light and the electrons, the heavy W and Z and Higgs, the quarks bound by the strong force, all of them leaving their faint mark on one tiny magnet's wobble. To measure it is to weigh the contents of empty space. That is the quiet wonder under this whole story. A particle that lives 2/millionths of a second circling a magnet ring at nearly the speed of light carries in the rhythm of its dying a record of everything the universe is made of. We learned to read that record to 12 decimal places, and when we did, the known particles accounted for the wobble almost perfectly. The vacuum, weighed this carefully, turned out to hold no stranger right now than the ones we already know. There is something humbling in how the answer arrived. We wanted nature to surprise us, to reveal a new force hiding in the muon's wobble. Instead, the lesson was about ourselves, about the limits of our own calculations and the patience required to push past them. The anomaly measured not a gap in the universe, but a gap in our arithmetic, and closing it was an act of human persistence as much as discovery. That is a less dramatic story and a truer one, and yet the work is not finished, and that is its own kind of hope. The clash among the collider experiments remains unresolved. New measurements are coming from Japan and from CERN, and the lattice calculations grow sharper still. The muon is still listening to the vacuum, and we are still learning to hear what it hears. Should some future measurement turn up a fresh disagreement, the door to new physics, only just eased shut, could open again. So the particle nobody ordered turned out to matter enormously, not for anything it builds, but for what it reveals. Its uselessness made it a perfect probe, light enough to store and watch, heavy enough to feel the deep vacuum, faithful enough to measure to absurd precision. In chasing its faint magnetic wobble, we tested the laws of nature about as hard as they have ever been tested, and they held. The next time you feel a magnet tug at a steel door, you might remember that the same force, traced down to a single dying particle and measured to 12 digits, became for 20 years our best hope of finding something new, and then became, instead, one of the most precise confirmations that we understand the world we are part of. The crack closed. The wonder did not. It only grew quieter and deeper and waited for the next question.